Swayam Prabha. Digital India. Educated India.
So, welcome back, and this is lecture number 37. We will be continuing our discussion on system of linear equations, and in particular today we will look for the solution techniques, that is the Gauss elimination method. So, we will be talking about this Gauss elimination method, and there we will see that how to get the solution using this very systematic elimination technique. And with the help of the same, we will also talk about the consistency of the solution. That means about the existence and non-existence of the solution. With the help of this technique, we can identify whether the system has a solution and it is unique or it does not have a solution. All these identification we can also check with this Gauss elimination method. So, the system of linear equations, the solution methods, we have basically the other methods too, like the method of determinants you must be familiar with, or we call this Cramer's rule. So, with the help of this determinant we get the solution, and this is possible when we have a system where a unique solution exists. The same equation, the number of equations are the same as the number of unknowns, and the system has a unique solution. In that case, this is possible to get the solution of a rather smaller system of equations using this method of determinants. We have also the matrix inversion method, where this Ax is equal to b, this system we can solve once we have the inverse of the matrix. So, out of this Ax is equal to b, we can write down like x is equal to A inverse b, and once we have the A inverse, so we multiply by this b and then we will get the x. So, if we have the inverse of a matrix, we can easily write down the solution of the system. Now, this is a little more general case which we will be talking about, this Gauss elimination method. So, here we will be also dealing the cases when we have non-unique solutions, meaning infinitely many solutions, or the system does not have a solution. So, all these we can figure it out with this Gauss elimination technique, and we have iterative methods, that is the Jacobi and the Gauss-Seidel method for solving when we have a system of equations which is large in number. So, really a very large system. So, all these methods which we have, this method of determinant, Gauss elimination, inversion method, they actually fails, or rather they take longer time. So, we take these iterative methods. So, the first three methods falls into the category of the direct methods. The direct methods meaning that we get actually the exact solution of the system using these techniques, whereas here the iterative methods, they give us the approximate solution of the given system of equation. So, we will be talking about in this lecture about this Gauss elimination method, which is a very general one in the category of this direct methods, and we will be also talking about in this technique some elementary row operations. So, what do we mean by elementary row operations? So, we can interchange the ith and the jth row of a matrix, and if going back to the system of equations, because for the system of equations we are writing the matrix A. So, changing this row is nothing but just the writing the second equation, for example, at the first place and the first equation at the second place. So, it has nothing to do with the solution, and that exactly in terms of the elementary row operations we will be doing with the matrix, that we can interchange any two rows of the matrix. The second one, we can multiply the ith row, means any row, by a non-zero number lambda, and this is precisely equivalent to saying that we have a we have those equations and we are multiplying any equation by some number, and again the system, the solution of the system will remain the same with that operation. So, in terms of the matrices, we talk about this row operation, that Ri now the ith row has become like lambda times Ri. So, we have just multiplied lambda, a non-zero number, to the equation Ri. Here addition to the lambda times the jth row to the ith row. So, what we can do, that we will multiply the jth row by a number lambda, again non-zero number lambda, because if lambda is 0, then we are not adding anything to this Ri. So, this lambda times the jth row, and we will add this to the ith row, and in terms of the operation we write like, now the Ri has become as Ri plus lambda Rj. So, we have added lambda times this Rj to Ri. So, the row, so R means the row. So, the ith row we have added this lambda times this jth row, and the new Ri will come up. So, here these are the elementary row operations which we will be using for this Gauss elimination method. Let us explain this with the help of simple example, and then perhaps in the next lecture we will go for more general problems. So, here we take a very simple example. So, we have three equations, x 1 plus x 2 plus x 3 is equal to 4, and 2 x 1 plus 3 x 2 plus x 3 is equal to 7, and the third equation we have x 1 plus 2 x 2 plus 3 x 3 is equal to 9. First, we write down this equation in this matrix form, where we also augment this right hand side of the equations 4, 7, 9. So, the right hand side here I will be basically doing precisely what we do in Gauss elimination method, and the left hand side we will be doing the same thing with the equations directly. So, it is easy to understand that this Gauss elimination is nothing very complicated, but it is like eliminating the variables in a systematic fashion. So, here we have first, that will be the first step, that we have to write this combined matrix, or so called the augmented matrix in this form. So, we have the coefficient matrix, that is our matrix A. So, if we write down this system of equations into Ax is equal to B form. So, this A is going to be in this case 1 1 1, and then we have 2 3 1 and 1 2 3. So, this matrix, and then the right hand side vector is 4 7 9. So, these two, the matrix A and the matrix B, basically have all the information of the given system of equations. And what we do in the augmented matrix, we basically collect this A here. So, this is precisely the A 1 1 1 2 3 1 and 1 2 3, and this B we have augmented here with the same matrix as extra columns. So, the 4 7 and 9. So, this matrix we call as the augmented matrix. So, here what we do now, the left hand side with the equations, as I said, I will show everything with the equation, and then we will translate into the form of this matrix and so called the Gauss elimination technique. So, here what we are doing now, with the help of this equation number 1, we are trying to eliminate this x 1 variable from the equation number 2. So, what we are supposed to do actually, that if we multiply this equation 1 by 2 and then subtract this equation from this equation number 2. So, we have now the equation number 2 will become the equation number 2 minus this 2 times and the equation number 1. So, this we have done this manipulation here. So, 2 times the equation number 1, and then we subtract here. So, this will cancel out. Here we will get 2 x 2 and then here 3 x 3. So, when we subtract, we will get x 2 here, and then we have 2 x 2 and this x 3. So, we will get minus x 3, and then here 7 minus 8. So, that will be minus 1. So, we have just done this operation that we have multiplied equation number 1 by 2, and then this is subtracted from equation number 2 here. Now, same thing we will be doing with this equation number 3. We want to again eliminate here as well this x 1. So, but this is easy again with the help of equation number 1. So, here we will just subtract the equation number 1 from equation number 3. So, we will get simply here x 2. So, 2 x 2 minus x 2, 3 x 3 minus x 3, that is 2 x 3, and 9 minus 4, that is 5. So, we have a new system here where we have eliminated from equation number 2 and equation number 3 the variable x 1, and we will continue this process actually now from equation number 2 and equation number 3. So, with the help of equation number 2 now, so equation number 1 we have taken to eliminate x 1 from 2 and 3. Now, we will consider equation number 2 to eliminate x 2 from equation number 3. That will be the next step. But now, before we go to the next step, let us look at this in terms of the matrix. What we do? We will be doing now this elementary row operation, that this row 2 will become now row 2 minus 2 r 1. So, 2 times the equation 2 times the row 1 and this r 2. So, r 2 is 2 and then minus 2 times this one. So, 2 minus 2, that is 0. So, this will become 0 there, and here again, and we will have another operation which was corresponding to this this elimination from the third equation. We will do simply the row 3 minus row 1. So, these two elementary operations we will be doing now, which is parallel to what we have done with the equations. So, what we will get? So, when we do the first operation here, r 2 minus 2 r 1. So, r 2 minus 2 times the r 1, the equation number 1. So, here we have 2 minus 2, that is 0, then here 3 minus 2, here it is 1, and 1 minus 2, that is 1 here, and then we have 7 minus 8, that is minus 1, and at this place just we are subtracting row 1. So, here 1 minus 1 0, then we have this 2 minus 1 1, and then 3 minus 1, this is 2 here, and then we have 9 minus 4, that is 5 here. So, that is the elementary operation we have made here to reduce this augmented matrix into this form. And now, the next one, as I said before, with the help of equation 2, we will eliminate x 2 from the equation number 3. So, we have this first equation x 1 x 2 x 3 is equal to 4. We have the second equation, we will not touch, x 2 minus x 3 is equal to minus 1. And now, what we will do, we will eliminate this x 2 from this equation number 3. That means, this equation number 3 minus equation number 2. So, this will become 0. So, no x 2. Here when we subtract, this will come 3 x 3, and here it will come 6. So, we have this system now, where from the third equation x 1 x 2 is removed, from the second equation x 1 is removed, and the first equation is intact as before. So, again the same operation here in terms of the row operation, we will write like r 3 minus r 2. So, now the equation number r 3 will become r 3 minus r 2. So, we write in this form. So, we have the first two rows as it is, first two rows will be there, and then the third one we will have here r 3 minus r 2. So, we are subtracting the row 2. So, here naturally the 0 minus 0, here 1 minus 1 is 0, 2 minus 1, that is 3, and 5 minus 1, that will be 6. So, we have this augmented matrix corresponding to this equation. And now, the next one. So, we have this reduced system here or corresponding augmented matrix, and now this is the one step which we have to do in this Gauss elimination, to start with this augmented matrix and to reduce into this form which we call as echelon form. So, this is we will be continuing this discussion in the next lecture, what is exactly echelon form in general. So, in this case, roughly speaking, now we have to see whether we got this echelon form. So, always we will have this structure for the echelon, this step like structure for this echelon form. So, here something non-zero, everything 0, then here also, then everything 0, and then everything 0 here, and the left hand side naturally. So, we have this echelon form of the system, and once we reach to this echelon form, we can get the solution very easily. So, first let us see with the equations how to get the solution now. So, the solution will be from the last equation, we can directly write down our x 3. So, the x 3 will be 6 by 3, that is 2, and from the equation number 2 we can get now x 2 is equal to minus 1, and then this x 3 will be added, that is 2. So, we will get 1, and from the equation number 1, since x 2 and x 3 is known, we can get x 1 as 4 minus this x 2 1 and minus x 3, that is 2. So, 4 minus 3, that is 1. So, we got the solution here. Once we have this form, we have to do only little manipulation to get the solution x 3 2, x 2 1, and x 1 is 1. What we call in terms of the Gauss elimination, we call it this back substitution, that is the actually the third step. So, the first step was putting into this your matrix and the right hand side vector into this augmented matrix. The second one is to the reducing to this echelon form by doing these row operations. The last step of the Gauss elimination is going to be back substitution, where we will get the solution of the system. So, back substitution, we will start from the bottom here with the 3 is equal to 6. So, the last equation, this is the last equation which says 3 x 3 is equal to 6. We should always keep in mind that corresponding to this we have actually the system of equations here given in the left. So, here we have actually 3 x 3 is equal to 6, that means x 3 is 2 here. Then this x 3 is known, then from this we will go step by step to up now. So, here from this equation we will get x 2 variable. So, x 2 will be minus 1 and then plus this x 3 which is 2, and then we will get 1. Now, we will go further up here to x 1, and then we have a 4 minus x 2 minus x 3, 4 minus x 2 and minus x 3, and that is equal to 1. So, we have x 1 is equal to 1, x 2 is equal to 1, and x 3 is equal to 2. So, we get the solution out of this back substitution once we have this echelon form of the equation. There are few more points to be noted here, and we will explore them in the next lecture again. So, what we have observed that we have got a unique solution. We have got a solution of the system as 1 1 2, and indeed this is the unique solution of the system. We do not see any other possibility directly getting the solution from the equations. But what is now we are going to introduce this that these numbers here in this first row or in this first column, this is called the pivot element. This is called the pivot element, and pivot element is always non-zero element, and below this everything should be 0. And now, here when we come to the next row or next column, this number is again pivot, because everything here to 0 and left to also 0, and also in this submatrix everything is 0. Going to the next, this is also a pivot element, because this is non-zero and everything left to 0, and there is nothing here because the matrix was this 3 by 3. So, these such elements, such non-zero elements will be called pivot, because they play a very important role now discussing about the consistency of the solution, about the existence non-existence of the solution. So, if we have like written here the number of pivots. So, here how many pivots we have? We have 1 pivot, we have 2 pivot, we have 3 pivots. We have 3 pivots in our system here, in our matrix, in our this augmented matrix. So, the number of pivots here is equal to number of unknowns. How many unknowns do we have here? 3 unknowns, x 1, x 2, x 3. So, this number of pivots is equal to the number of unknowns then we have exactly the unique solution. This is the case of the unique solution, because our number of pivots is equal to number of unknowns, or in other words we say, because each column is parallel, each column is associated with one variable. So, the first one with x 1, this is associated with the x 2, this is associated with the x 3, because if you remember, we can write down this Ax is equal to b, I mean this product here in terms of this column here 1 0 0 multiplied by x 1, and then the second one will be multiplied by x 2, the third column will be multiplied by x 3. So, this first column is associated with x 1, here this is with x 2, this is with x 3. So, if the number of I mean each column has a pivot, we can in other way we can put it as that if each column has a pivot, in that case the solution will be a unique solution. So, every column has a pivot, and this is exactly the case when we have the unique solution. So, we will be exploring a little more on this pivots, and this is just a very basic introduction to this concept here, and we are considering only this 3 by 3 matrix. So, we will be talking about in the next lecture more about these pivots and echelon form. So, now going to the example number 2, we have changed the example now. So, this augmented matrix is taking this form, and by doing those elementary transformation which we have done earlier, the same transformation, because there is only little change in the matrix, we will be again trying to make this element 0 out of the first row. That means we have to do we have to subtract from this row 2 times the row 1. So, this is exactly written here r 2 minus 2 r 1, and to make this 0 with the help of the row 1, we have to just subtract the row 1. So, with these two operations we will get this form 1, and then we have the 0 0. That was the objective in this algorithm, to eliminate this x 1 variable from the equation number 2 and equation number 3. And now, the next objective is that using the equation number 2, we will eliminate x 2 from the equation number 3. So, here that means r 3 will be now r 3 minus r 2, and so we have, when we subtract this will be 0, this will be also 0, and this will be 6 here. So, what do we see now? It is something different than the previous case. If we look at this closely to the last equation, what are we getting from this last equation? We are getting here, so 0 times x 1, 0 times x 2, 0 times x 3, that is exactly what we have here, x 2 and 0 times x 3, and the right hand side is 6, meaning what we are getting, that 0 is equal to 6. This is what we are getting from the last equation, and that is the point where this Gauss elimination technique, or this reduction to this echelon form helps, because here we can now observe that there is an inconsistency in the system, because we should not get 0 is equal to 6. So, by reducing to this echelon form, we have also realized that the given system is inconsistent. Inconsistence mean again that it has no solution, it cannot have a solution here. So, by just reducing to this echelon form, we observe that the solution has no that the system has no solution, because from the last equation we are getting 0 is equal to minus 6. So, by observing this, we conclude that this system, the given system, has no solution, and in other words, in terms of the pivots, we call that the rightmost column has a pivot, because now this is the pivot here and this is the pivot in the second row or in the second column. The third column has no pivot, because this cannot be a pivot, because this is a 0 element, the pivot has to be a non-zero element. But looking at this number here, this is a pivot. So, it satisfies that everything left to the 0 and there is nothing to go to the bottom. So, we have this rightmost column has a pivot. So, which is the case exactly of the inconsistency, or the system has no solution, because this rightmost column has a pivot. This should not happen. The pivot should be there in this main matrix here, not in this rightmost column, which corresponds to this right hand side vector B. Okay, so this is the case of no solution and the equations are inconsistent and hence the solution does not exist. Now, we will go to the third example, which is again slightly changed. So, here, but we will be doing the same operations, this R 2 minus this 2 R 1 and R 3 minus this R 1, the same operation, because the aim is to eliminate x 1 from equation number 2 and equation number 3. So, by doing so we got this, and then the further again the same operation, because this equation I mean this row 2 we want to get rid from equation from row 3 this element 1 here. So, we will just subtract. So, R 3 will be R 3 minus R 2, and in that way we will get this 0 here, also 0 and 0. So, now this is different than the previous case. We are not getting anything like 0 is equal to 6, we were getting the last equation is completely 0. So, 0 is equal to 0, there is no problem, or in other words we do not have pivot in the last column here, because what are our pivots? This is a pivot elements, and as I said, they play a very important role in discussing several properties of the vector and matrices. So, here this is pivot, everything 0 here and there is nothing left. Now, coming to the right one, this is pivot. See, this is not the pivot here, because the left you have a non-zero element. So, for the pivot it has to be 0 to the left and also to the bottom, and everything to the left has to be 0. So, what we have this pivot here, we have this element as pivot, and now going to the column number 3 or the row number 3, we do not have any pivot. So, no problem. So, but at least the last the rightmost column also does not have a pivot. So, the system is consistent. So, the system is consistent means we will have solutions, and indeed in this case, when we see that the equations are consistent and this number of pivots are less than actually the number of unknowns. So, in this case we are getting only 2 pivots and there were 3 unknowns. So, this is the case where we have infinitely many solutions, because in the case of unique solutions the number of pivots will be equal to the number of unknowns. So, in this case we will have infinitely many solutions, and in terms again a very systematic approach to solve this when we have this case of infinitely many solutions. So, this column has a pivot, this column has a pivot, the third column does not have a pivot, and as I said, this we say this is corresponding to x 1, this is corresponding to x 2, and this is corresponding to x 3. So, here since this x 3 corresponding to the x 3, the third column does not have a pivot, we call that this x 3 is a free variable, because corresponding to this x 3 the column does not have a pivot, and we call this like a free variable. Free means we can choose this as we want. So, this is exactly the point where we are entering into the discussion of the infinitely many solutions, and since this is free variable, so we can choose anything we want, and that is what we will do now. So, here the number of pivots is less than is equal to number of unknowns, because there are 2 pivots and there are 3 unknowns, and the number of free variables will be precisely the left one, because this is occupied. Here we have pivot, the x 2 has a pivot, but x 3 does not have a pivot. So, this is free variable. So, number of free variables will be n minus r. So, n is the number of the columns there in this main matrix here A, or the number of unknowns, and minus this r, that is the number of pivots. We give this name to the number of pivots. So, now what we have our system which is reduced in this form, and where x 3 we have denoted as marked as free variable, and then we can choose this x 3 some alpha is a real number, and then once we have x 3, then from equation number 2 we will get x 2, because these are the dependent variables now. So, the x 2 will be minus 1 and plus 1. So, plus alpha minus 1 and plus this x 3, that is alpha. So, minus 1 plus alpha, that is our x 2, and we have x 1 again from this equation number 1, 5 minus 2 alpha. So, which we can write down in this form x 1 x 2 x 3, x 1 x 2 x 3, all the constants from every component. So, x 1 has 5 as constant and this minus 2 with this alpha. So, here we have minus 1 and then with alpha we have 1, and this the from x 3 equation we have 0 as constant and this alpha with this 1. So, this is the solution of A x is equal to 0, and this is null space, which we will call as null space, and more discussion on this we will have a little later, but the solution of this A x is equal to 0, and that is a very particular structure. Here we do see, once we have written the solution here, it has two components, one without this alpha and the other one with alpha. And this part here 2 minus 1 1, this exactly satisfy A x is equal to 0, and if it satisfy A x is equal to 0, the alpha times this also satisfy A x is equal to 0, because this alpha is just a constant, and if x satisfy this A x is equal to 0, A into alpha x will also satisfy A x is equal to 0, and this the solutions of this A x is equal to 0, because there are so many solutions here for each alpha you take 1, you take 2, you take 1.5, anything. So, that is exactly the solution of A x is equal to 0, and this later on we will come to this is called the null space of A. So, null space will be nothing but the solutions, all solutions of this A x is equal to 0 together will be called as null space. Here this constant part without alpha, this is one particular solution of given system A x is equal to 0, sorry, A x is equal to b. So, this 5 minus 1 0 will satisfy our equations, and this minus 2 1 1 or multiplied by any number, this will satisfy A x is equal to 0, that so called the homogeneous system of equations corresponding to our given system. So, homogeneous means the right hand side we have set to 0. So, this is a very special structure we will be talking about more later. So, always we will have that this our x, we can write down x p. So, one particular solution of the given system plus this the solution of the homogeneous system when we set the right hand side to 0, and one can easily check that this 2 minus 2 1 1 actually satisfy when we have this homogeneous one, that means the right hand side 0. So, this minus 2 1 1, so here minus 2 1 and 1, so this is equal to 0, it satisfies. So, it will satisfy all these three equations, this part, and any number also we can multiply to this. It will not affect because the right hand side is 0. So, this part is exactly the solution of the A x is equal to 0 corresponding to this A x is equal to b equation. So, this part here is corresponding to A x is equal to 0, and this is one particular solution which exactly satisfies this A x is equal to b equation. So, more on this we will continue in our next lecture. So, what we have seen a very basic introduction to this elimination technique, and in particular very important is this echelon form which we have seen at least for this 3 by 3 system, and based on this echelon form we can talk about the solution, we can talk about the consistency of the solution or inconsistency of the solution. So, all these cases of unique solution, infinitely many solution can be discussed with the help of this echelon form. So, these are the references used for preparing the lectures, and thank you very much.